Hey guys, welcome back. We're going to do an example with vapor pressure with propane. So propane has a normal boiling point. So that's important. Normal boiling point at negative, right, at negative 42 degrees Celsius. And it gives you the enthalpy of vaporization of 19.04 kilojoules per mole. Here's your question. What is the vapor pressure of propane at 25 degrees Celsius? All right. So our equation that we just did. All right. So our Clausius-Clapeyron equation would be the natural log. All right. We got P1 over P2 equals delta HV over R 1 over T2 minus 1 over T1. All right. So there's our equation. All right. And let's put this together. P1 equals P2 equals delta HV equals R equals 8.3145 joules per mole Kelvin. T1 equals and T2 equals. All right. We're looking for a vapor pressure. So I am going to look for P1. I want to look for P1 because it's on top. I like solving for the variable on top better than one on the bottom. So P1 is going to be my question mark. That is what we're going to find out. So P2 then, P2, right, is normal. Well, what is normal? Normal would be 1 ATM, correct? So that's going to be 1 atmosphere. Now P2 has to go with T2, right? And that's negative 42 degrees Celsius. However, I can't keep it in 42 degrees Celsius, right? I have to change that to Kelvin, right? So we have to add 273, right? And so if I add 273 to negative 42, I get 231 Kelvin. All right, so that's T2. T1, 25 degrees Celsius. I have to add the 273, and that is 298 Kelvin. All right, and delta HV was 19.04 kilojoules per mole. All right, now I just got to remember that we have kilojoules there and joules there. All right, and so now we can plug in and solve. Now, maybe you're good enough to rearrange the variables and then plug in the variables and solve. If you can, I would feel free to do that. In fact, right now I would pause and do the problem and then come back to it and see if you got it right. But I'm going to put the numbers in and then go from there. All right. So the natural log. Oh, I don't want red. I want natural log. We're looking for P1. P2 was 1 atmosphere. Equals. Now I'm going to make this 19.04 times 10 to the third joules per mole. All right. I'm taking the kilojoules to joules. I just converted. So there I took kilojoules to joules. I did that up top. The bottom is R, then 8.3145 joules per mole Kelvin. Sorry, that's a K. And our temperatures, T2 was 231 Kelvin, and T1 is 298 Kelvin. All right, so first, it looks like I'm going to have to do everything over here. All right, so I'll do the natural log, P1, and I'm looking for P1. Let's re-highlight that. That's what we're looking for. Over 1 atmosphere equals, so if I do this in my calculator, I'm going to take 19 0.04 times 10 to the third divided by 8.3145 times 1 divided by 231, and I'm using parentheses for that, minus 1 divided by 298, close the parentheses, and I get 2.2288. And it keeps going. Units. Well, let's look. Joules are gone, moles are gone, and Kelvin's gone. Oh, there's no units because atmospheres. Now, the problem I can't just multiply, right? That's all in the natural log. So I don't know if that was clear or not. Maybe that's more clear. The natural log of everything. How do I get rid of that natural log? Same button on most calculators. It's the E, right? Okay, if that makes sense. So E and natural log, they're inverses of each other. So in my calculator, I have natural log as a button. I do second log, natural log is e to the x, and it's 2.2288. I get, all right, what do I get? I get P1 is equal to over 1 atmosphere is equal to 9.2, let's stay in the lines here, 9.2887. Well, I just have to, I kept that green. Let's keep that green. Now I just got to multiply by 1 atmosphere. So that means P1 is 9.2887 atmospheres. And if we go back, I have 2 sig figs. So that's 9, why are we writing? 9.3 atmospheres. And that would be my answer. Right? Now, 9 atmospheres, that seems pretty high, 9 times the atmospheric pressure, but that kind of actually makes sense. Why does that make sense? Well, if it boils at negative 42 degrees Celsius, at 25 degrees Celsius, which is much warmer, it should be a gas. And that kind of makes sense. All right, so there's a good example for that. If you have any questions, let me know. Otherwise, we'll see you next time, guys. Take care.